Hello and welcome back. Some enrichment and quite advanced today. We're going to look at series plus limits equals question mark. So we're going to actually attempt to find the following quantity. Okay, this is actually a follow-up on a lecture that I've done a little while back, so it triggered me to actually do another example which is related, but I'm not going to give you a clue yet what this is all about. We're trying to find the limit as n tends to infinity of this particular quantity. N is 1 over n plus 1 plus 1 over n plus 2 plus 1 over n plus 3 plus dot dot dot, and we're going to finish with 2n minus 1 plus 1 over 2n. So the question is, what is the limit of this finite series, if you want, in there as n tends to infinity? Okay, first of all, the first thing to notice is what's the pattern here. I'm kind of like losing it. I follow it here, but I'm losing a little bit there. Well, it's actually, if we try to follow it, there's always an n at the bottom. So let's write this n from these denominators, and therefore that should be n plus n minus 1, and then we have a n plus n. So this is basically our pattern. Okay, maybe we should really write it in compact notation, maybe, because at the moment I don't find this particularly helpful. Maybe the sigma notation might make it a little bit easier to see. So this is exactly the same as the limit as n tends to infinity of, I'm going to put in sigma notation. So all our terms have an n at the bottom left, and careful for the sigma, this is not a dummy variable, it's actually a constant, there's always an n in there, and what is changing is this number here, 1 2 3 4, and we're gonna need a dummy variable. We could have put r, but I prefer to put I for this one, for familiarity with what we're about to connect. We tend to use I for this type of work. It will all be revealed in a little while. So we got from I is equal to 1 and into n, just checking that this is correct. N plus 1, n plus 2, n plus n when we finish to the other end. And of course we try to find the limit of this as n tends to infinity. Okay, I'm going to wrap off this particular series. This is basically our objective. So it would have been given like this and say, okay, find this limit. So we wrote in sigma notation, and now we're trying to look for clues of what we're going to do. And I wrote up there, series plus limits equals question mark. What is the missing question mark in there? Well, the answer is most of the time, not always, but when I see limits and series together, I'm thinking integration. Because an integral, definite integration, of course, not with limits, because of course what the definite integral is basically the limit of a convergent series, basically. And if you want, I can write integration, and of course this will lead me to perhaps going into Riemann sums. I hope I'm spelling it correctly. Riemann, does it have two m's or two n's? And sometimes I'm mixing the I and the E there. I hope I spelled Mr. Riemann correct. Riemann sums. Okay, and now I can tell you how this question was made. When I gave a lecture a while back on Riemann sums, you perhaps need to look at that particular lecture first. I thought to myself, I'm going to put another question which is related to that, just for more practice or more understanding. So this is now targeting perhaps either undergrads are familiar with, obviously through their analysis courses with Riemann sums, or somebody who's doing a lot of reading and of course they have seen this before. So this is now what we're trying to find. I'm going to just do, first of all, a little bit of work on the definitions from Riemann sum. So this is what a Riemann sum is. So the integral from a to b of a function f of x dx is the limit as n tends to infinity, and I hope I can fit it there because I wrote too far to the right. Sum from I is equal to 1 to n is f of x I delta x. and we need to define what is this xi and what is the delta x. Delta x is the width of the rectangles when we're doing the Riemann sums, which is b minus a over n. And your xi is the height, actually it's the x coordinate, which we're going to need to find the height of the ith rectangle. So we need to start from a and go I steps of delta x along the x-axis. So this is now our delta x there, and this is our xi in there. So perhaps we should just write it again and say, okay, the integral from a to b of f of x dx, and I'm panicking now that I might not have enough space to put these things in there. So I'm going to squeeze it as much as I can, limit as n tends to infinity. Then we got the sigma. I will avoid using brackets. I should really have put a bracket here, but it will take too much space. So now I have f of xi. What is f of xi? Actually, I'm going to do it in 2 steps and move a little bit more to the left on the next line. So this is f of xi is a plus I delta x, and my delta x is, of course, shall I leave the delta x and just put it at the very end? It doesn't really matter. Let's put this delta x in. That's this one here. B minus a over n. And that should be the argument of the sigma. And the limit is all of this. So let's leave a bit of space in all of this. I'm going to thread onto this cable in a second from the microphone. Let's move it out of the way. And this now will give, I'm not going to write this again, I'm just going to move it the equal here because I'm going to need the rest of the board to do my work there. So this is now just writing this limit in full. Limit as n goes to infinity. Sigma, I didn't put there, obviously, from I is equal to 1 to n is from I is equal to 1 to n. F of a plus I b minus a over n, because that's my delta x here, times a b minus a over n. So this again inside the sigma, all of this. And if we look at the dummy variable on this sigma is running in I, n is a constant, and all of this is a constant, and therefore we can move this quantity outside the sigma. There's no I in it at all, but of course we cannot move it outside the limit because the limit is in n, and this has an n in it. Okay, so I'm going to write the limit as n tends to infinity. Let's put all the arguments in. So this is now the b minus a over n. Then I'm going to have the sigma operator from I is equal to 1 to n, and this will have f of a plus I b minus a over n. And this is now closing the argument of the limit, and the f of all of this is inside my sigma. Okay, all of this work looks very, very scary. If you look at Riemann sums and that particular lecture, I have explained all these things, and I've done a simple example to actually illustrate this. So now somehow we have a limit and a sigma here, and we got a limit and other bits there. So we need to relate this expression with this expression somehow, so we can identify the a, the b, a few bits and pieces. So I'm going to manipulate this particular limit a little bit. First of all, I'm observing inside the limit I've got a quantity something over n, which is at the front of the sigma. So at the moment I've got this n here. So what I can do is I can factorize the n, not obviously in front of the limit because that's got an n, is running in n, but I can certainly pull a 1 over n in front of the sigma notation. So I 1 to n, and I'm going to write this as 1 over 1 plus I over n. And the rationale for this, again, just checking, I'm comparing the two expressions, and I'm saying, well, this is the something over n that I want in there. And I'm going to do another line, which is equal to, rewrite this argument a little bit better, the limit as n tends to infinity, 1 over n sigma I to 1 to n, and this I can write as 1 plus I over n to the minus 1. That's just that. And now again I'm looking at these two expressions which are practically side by side. Something over n, b minus a over n, and then I've got a 1 plus I times 1 over n again if you want, which is of course the same thing like that if you think about it. So let's try to make some comparisons. Let's say this one here, the 1 over n, is the b minus a. The b minus a, of course, is the difference between the two limits in an integral to be found. So we're actually saying b minus a, by direct comparison, has to be equal to 1. Then what is this 1 here? If we're comparing it now with the function, of course, is the 1 over x function, because it's something to the minus 1. This a must be this one here if we try to match it. So if this is a 1, if the a is 1, then quite clearly for a to be also 1, the b must be equal to 2. So 2 take away 1 is 1. So let's use a red pen and start putting some of these things here. So this is your b minus a, that's your 1. This is your a here. This is your n, obviously, as we see it. And we got, of course, let me just rewrite it a little bit, not massively, but just to actually see. This is the I that we got in there. I'm going to write it separately. I times 1 over n. It's exactly the same thing. So it will help us with the comparison a little bit. So this is the I that we see in there. And of course, again, we got 1 over n, which is the same as 1 over n, which is the same as b minus a over n. So everything kind of fits now. And I forgot the minus 1 there, to the power of minus 1. So b minus a, that's my 1 in there. And I have a perfect match. According to what this thing here is, taking it back, this limit is the integral, the definite integral of f of x from a to b. So clearly ours must be, again, a definite integral from 1 to 2 with respect to x of what function? The function is something to the minus 1. That's your f of this argument. The function is to the minus 1. And x to the minus 1, I can write it like this. So this particular limit that we're trying to find, I'll rub it off how it was given in the beginning in explicit form. This quantity here is given by exactly this integral. And what is this integral? This integral is, of course, 1 to 2. X to the minus 1 is 1 over x dx. Very easy integral to do, which of course is the log of x. I'm not going to put mods because the limits are both positive. 1 to 2, which will give you log 2, take away log 1, and the log of 1, of course, is 0. So in fact, the quantity that we're trying to find, the limit of this series as n tends to infinity, is in fact log 2. Quite a challenging question. I don't know if you followed all the stuff that I've done up there. That's actually using Riemann sums backwards. So we actually using the integral as a given now to actually find the limit of a sum. And this particular sum comes to log 2. You can check it in an algebra system. I don't know if Wolfram or whatever systems you're using, Mathematica or whatever, if you that can evaluate this kind of stuff. It will actually give you log 2. I hope you enjoyed it. I hope you followed it. It was not easy to explain because I haven't done this kind of work for a very, very long time, and I'm a little bit rusty. And I will see you very, very, very soon. And who's laughing now?